Hello again, everybody. Welcome back to Grade 12 University Physics. So today we're going to talk about, it's not really review, it might be review. It's a review of some mathematical models and sort of how we can manipulate them to do analysis. So what do I mean by all this? So you've learned a bunch of relationships in math class in grade 11 functions, right? So we've figured out these ways that we can mathematically represent relationships. Things like linear relationships, quadratic relationships, inverse, and square root. I'm just going through them quickly. Now, the, the thing about physics, right, is we're looking at the universe. We're looking at phenomena. We're looking at how things happen, how something is related to something else. And um, the language of mathematics is very powerful in allowing us to um, be able to talk about relationships easily using mathematical relationships, using these things that we've learned so far. Right? Things have proportionalities. Things can be proportional in a linear way. As one thing increases, the other increases proportionally, and we can have a linear relationship. So, for example, here, this is a linear relationship. Things like this happen in nature a lot, right? As one thing goes up, another thing goes up, and we can model this with y equals mx plus b, right? We have our uh, y equals mx plus b from grade 9 math, right? The b was the uh, y-intercept, and the m is the slope, the rise over the run, right? And that way we're able to mathematically talk about that, right? We can use a lot of words, but something like this is much more efficient, much quicker, it says all the important information. In the same way, we can talk about quadratic relationships, where something increases as a square of the independent variable. For example, if I drop a ball, the distance that the ball travels in the downward fashion, so this is d down, with respect to time. Oh, sorry, you can't see that. Time is on the x-axis. As the ball falls, its velocity increases linearly, but its displacement increases quadratically. Remember, we had our plus 1/2 a delta t squared. So one of our kinematic equations. So as you can see, the distance increases as a quadratic with respect to time. Okay, and we can have other relationships like inverse relationships. For example, something like F equals ma, right? Newton's law. Acceleration is inversely proportional to the mass. As I increase the mass, I reduce like if this is m and a, I reduce my acceleration as an inverse. It's proportional to 1 over x. Or square roots. These are just the doing a quadratic backwards, right? We can have square root relationships. And the problem here is that mathematically, these things can be quite complicated. They can have finding coefficients and ways to, write these things algebraically can be complicated because, mathematically they're more complex. So if we're able to somehow trick my graph into being a linear relationship, I can just use the simple old y equals mx plus b. And we can do this. We do this by taking our graph, taking our data sets, and manipulating them some way to change our axis, which makes it a straight line. So for example, if I take a quadratic relationship, if I change my x-axis from x to x squared, if I take all my x values and I square them, I now end up with a linear relationship that we can express as y equals some coefficient a, my slope, multiplied by x squared. Because my x squared now becomes my variable. I've changed my variable from x to x squared. And this a, this slope, is just my rise over run for that line. Similarly, if my relationship is an inverse like this, if I change my x-axis to 1 over x, I end up with a linear relationship, right? This is y equals a. My variable now is 1 over x. So again, I can just calculate the slope. I can get Excel to spit out a linear trend line, and I can get my a. And this will end up being like y equals a over x. Right? It's more complicated. It'd be very, very difficult to figure out what that a is. We have to find points on here, and then plug them into my equation, and do some algebra stuff. Here, I just get a linear trend line from Excel. I'll show you how to do that, and we're good to go. Also, again, if I have a radical expression, I can take my variable, change it to root x, and again, my slope becomes just my coefficient here, my proportionality coefficient, just becomes the slope of my line. So just being able to manipulate these things quickly allows us to end up with a mathematical relationship. So if that's kind of complicated or difficult to see just by talking about it, let's do an example. Okay, so let's say here we got Chris was gone on a ski trip. Okay, and comes up with this data. So we have time going up by seconds, and we have velocity in meters per second. Okay, so we're going to plot this data. So let's switch over to Excel. Okay, let's go to Excel. So here, this data set is on the Weebly. It's called Straightening a Relationship Data or something like that. So and it contains also the assignment data. Okay, so if you don't have to write it all out, it's all there for you. And I'll show you how to manipulate this data as well in a sec. But let's say here, if I just graph these, so I'm going to I'm just in Excel. Okay, this is time, velocity. I'm just going to click and drag to highlight all my data. I'm not highlighting the top here. I'm going to go insert, and I'm going to insert a scatter plot up here. This is scatter. Okay, I'm not going to insert a line plot or anything like that, just the data. So if I click on scatter, here, I get all of my data. Okay, so as you can see, this is probably quadratic. Okay, looks like a parabola, and that's not good, right? We don't want this. This is difficult for us to mathematically manipulate. Right? We can try to fit it with a quadratic relationship or anything like that, but let's not. Okay, let's get rid of this for now. Let's just delete that graph. What I'm going to do here now is let's go back to my data here. Let's see. So it looks as though things are happening as a square. Okay, so it looks like velocity is proportional to the square of time. Okay, so velocity is proportional to the square of time. So what I'm going to do then is I'm going to insert a space here, and I'm going to make a new column, which is going to be t squared. This is the square of the time. And I'm going to put this in, the units here is going to be meters squared per seconds. Oh, I got 2 seconds squared. Now that's going to be ugly looking because I'm running out of space. So let's make that bigger so we can see what the whole label is. Okay. Now I want to square all my times. Now I can use a calculator to do that, but Excel is a big calculator. So I'm going to take my cell right here. I'm going to say equals the one next to it, A2, and I'm just going to square it. So let's do that again. Okay, so if I just click on the cell and I go equals, notice this formula bar up here. Let's see, actually, wait a second. There, now we can see it better. Okay, so in this formula bar, there's a equal sign. So I'm going to just click on the cell again. If I hit equals, it puts it up in the formula bar. And I'm going to click on A2, and I'm going to square it. It equals, and that's squared 0. 0 times 0, 0. But I want it to repeat that. So I click on the little box next to here, drag it down, and it squared them all. Okay? So now I have t squared and v. So let's do that again. I'm going to take all my data, and I'm going to make a scatter plot. And look at that. now my, oh, whoopsies, I moved the table, the title. Okay, so I now have a linear relationship, and I can right click on the data point, click add trend line, and display on there, and I now have an equation, a linear equation, y equals mx plus b, for my data here. Now this graph isn't very good. I should put here, this is v squared. Actually, let's go v squared. I can now, here's a trick. If you want a superscript, hold down shift and control and plus, and that'll give you superscripts. Now hold control plus gives you subscripts, and if you want to go back to what you did, just do it again. So right now I'm in superscript mode, so I'm going to hit control plus again, and I'm in regular mode. So this is v squared versus t. Also, I don't have any labels, so we should add some titles, axis titles. This was, what's this? This is velocity squared. And the units on that were meters squared per seconds. Oops, squared. There. And my x-axis was time in seconds. Okay, so there I have a nice graph that shows me my relationship. And I have an expression here. So I can say v is equal to 0.25 t squared, right? Because my x-axis is actually t squared. So I've gone from my quadratic data to come up with an equation for this just using linear relationships. Okay, so it doesn't matter how complicated. It could be a cubic, it could be whatever. If I change my oh, sorry, this wasn't. No, I made a mistake. I apologize. This is not, this is just velocity on the axis. Why did I square that? This is just velocity in meters per second. My apologies. It's going too fast. And time was squared, right? All right, there we go. So it's v is equal to 0.25 or a quarter t squared. All right. So I can come up with my graph here. Or another way I can say this is that v equals 0.25 t squared, because my x-axis was t squared. Okay, and then from there I can actually answer number 3, which was what is the velocity at 12.5 seconds? Yeah, so I replace t with 12.5 seconds, and I come up with a velocity here of 39 meters per second. Okay. Now, just quickly, what is the units here, though? So what was 0.25? So let's go back to my graph here. This is in meters per second. This is in seconds squared. So what's the units going to be for my 0.25? It's going to be meters per second divided by seconds squared. So that's actually going to be meters per seconds cubed. All right. So then, sorry, let's go back here. So when I actually go here, this should really be 0.25, sorry, meters per second cubed multiplied by 12.5 seconds. And this is all squared. So this is actually going to end up being, what was my number? 39 meters per second cubed multiplied by seconds squared. And then the two of them are going to cancel with 2 on the denominator, and I'm going to end up with 39 meters per second. Okay, so the units do work out. So we do have to be careful. I apologize. I should have written the units in there. When you do a math problem, when you do these physics problems and they involve this sort of math, make sure you write the units in. I apologize. I didn't do that there. That's my mistake. Okay, sorry. Add the units so that you can see that if the units don't work out in the end, it's a really good indication that you did something along the way to make a mistake. Okay, so if you put your units in, it's a good check as long as you go along. The units should always work out. Okay, and if you don't have units at the end of your problem, that's a big problem. Make sure you always have units at the end of your problem. If you don't, I'm going to assume that those units are cats per donut or some other trivial unit. Okay, and then the answer will not make sense. Okay, my answer is 5. 5 what? 5 thumbs? 5 cats per donut? It's nonsensical. Without units, a numerical answer is nonsensical. So please make sure you always, always, always have units. Okay. So, oh, sorry here. What's this? Chris is traveling at 140 kilometers per hour. How did I calculate that, by the way? I'm just gonna erase this for now. How did I get 140 from 39? Do you guys know the trick? All you have to do is memorize the number 3.6. Okay, if I have meters per second and I have kilometers per hour, if I want to go from meters per second to kilometers per hour, I multiply by 3.6. And if I want to go the other way, I divide by 3.6. Okay, and just why that's the case, think about it for a second. So kilometers per hour. So a kilometer is 1,000 meters, and an hour is 3,600 seconds. Okay, so this will reduce to 1 over 3.6 meters per second. Okay, so if we're going from kilometers per hour to meters per second, we're going to divide by 3.6. This is the same thing. 1 over 3.6 is the same as dividing by 3.6. And if I want to go the other way, I multiply. Just remember, kilometers per hour is always bigger, so we multiply to get bigger. If I want to go smaller, I divide. Okay, just a quick little tip there. Just remember, 3.6 is the number we want to multiply by or divide. 3.6, 3.6. Okay, so your homework here is a little bit more complicated problem. Okay, so I'll just go through it quickly and actually give you a head start. So we have a water tank, and it's filled at various depths and empties through several drains of different radius at its base. So some student has set up an experiment where they put different depths of water. So they went 1 centimeter of water, 4 centimeter water, 10 centimeters of water, and so forth. And they changed the radius, the hole that is coming out of the tank. A 1 centimeter radius, 2 centimeters, 3 centimeters, 4 centimeters. And then they came up with all this data. So they have 20 data points here. So when the depth was 1 centimeter and the radius is 1 centimeter, it took 20 seconds. So these numbers are the time to empty, t, in seconds, plus minus 0.1 seconds. The uncertainty in the time is 0.1 seconds. So then it took 20 seconds for it to empty. It took 6.9 seconds to empty when the depth was 30 and the radius was 4. So we have all this data set, and there's basically, you could think of it as 5 different data sets. You know, one data set here, another one here. All these columns are different data sets. Okay, and we want to find out a relationship between depth, radius, and time. Okay, we want to come up with some function. So time as a, why is it not letting me write? Yeah, there we go. Time as a function of depth and r. We need to find out what that function is, that relationship is. Okay. So what we're going to do is we're going to come up with a bunch of graphs. We're going to look at the relationship of different graphs. So let's go back to Excel here. On the second page, if you go down to the bottom, there's a second page here, and we can see I've written out all the numbers for you. So let's consider now, let's make graphs for, what does it ask us to do first? I'm going to, one second. So it's asking us to figure out, make a graph, of time versus depth for the different radiuses. Okay, we're going to put them all onto one axis. So how do we do this? This is a bit complicated. Okay, so I want to do times, so these are the times, versus the depths. So let's go for r equals 1. Let's highlight all the data here. And I'm going to insert, again, a scatter plot. And it comes up with oopsies. Let's put this over here. It's a bit big. Okay, so there's my chart. Okay, now this is going to be, what are we going to call this again? This is time versus depth. Let's add, go to the plus, add axis titles. Remember, this was the time measured in seconds, and the bottom here, this was depth measured in meters. So I should capitalize that. Okay, so this is my graph so far. Let's make it a bit bigger. I'm going to zoom out from my data just to make it. So there we go. Okay, so we want to now add the next data set to here. So this is where things get a bit complicated. Okay, so what you're going to do is you're going to right click on the plot area, and it says select data. So I'm going to go select data, and I get this scary looking thing here. And currently it's showing me that I have series 1, and it's highlighted. So this is showing me that I have these blue dots are represented by this series 1, but I want to add another one. So I'm going to go add. Actually, first, let's click on series 1 and go edit. And it's telling me that it's using CG as my data. Okay, so that's C to G. It's using these, and it's using 2 and 3. So 2 and 3. Don't worry about this. We won't be manipulating this. But I want to call, this was my radius of, what was the radius? This is R equals 1 centimeter, right? So that was my R equals 1 centimeter. I just want to give it a name, and you'll see why in a second. So I'm going to add now a new data set. And this one is going to be radius R equals 2. Let's go. R equals 2 centimeters. Okay? And now I'm going to click on the X values. I'm going to click in that area, and I'm going to go over to my data here, and I'm going to highlight my X's. My X's are depth from 1 to 30. Okay? And again, I'm going to go over here. Now, careful here. There's this 1 here. So let's erase the 1 and then highlight. Now, this is for radius 2. Highlight all of the times for radius equal 2. And notice they're there. There's all my data points on there, okay? All right. So I go, okay. So now I have another series, and then I can do the same thing. Again, add. This is going to be R equals 3. I'm going to click on my X values. I'm going to highlight 1 to 30. I'm going to go to my Y values, get rid of the 1 that's in there. And I'm going to go to the radius equals 3 data. And then I can do it one up. I can let you guys finish the 4th one yourselves. But all I'm going to do now is I'm going to click OK. And now that I've got to here, I can actually go add. If I add a legend, it actually tells me the labels. I had a capital R here. Let's go back into my data. Let's go back here, select data. R1, I have to rename that. Edit that. I had a capital. So let's make that a lowercase r. Whoopsies. Let's get rid of all that. R equals 1 centimeter. Okay, so now it's a lowercase r, so they're all the same. Okay, so now I've got a graph here of my multiple data sets. Notice it's not linear. So if you look, the next part of the graph, the assignment asks you now to change the variable to d, so the square root of d. So you're going to have to go into your table here. You might want to just copy it, paste it down here, and change these now to depth squared. Do the same thing for depth squared. Right, you can now, here we can do square root data, okay? And then we can put in our square root of these numbers. And then we can do the same thing, they'll end up linear, and we can come up with an expression, which is what it wants us to do. Find an equation relating t and d. All right, and then you can do the same thing for t versus r with 5 different values of d. Then you're going to straighten it. I won't tell you how to straighten it. You guys are going to have to figure it out yourselves. And come up with an equation. Okay? Come up with an equation for when d is 4 and an equation for when d is 20. Okay, I want you to come up with 2 different equations. And then put it all together. Come up with a formula. Okay? you're going to come up with a formula, and you might have to come up with a proportionality statement and then plug in some of your numbers into it to calculate the actual coefficient. Okay, so when we're done, we're going to have something like t is equal to, I told you already, it's going to be root d. I have no idea what the r, I don't know, maybe r cubed or something like that, and then maybe 4. I don't know. Okay, but we're going to come up with something like this. All right, and the last thing you're going to do is you're going to explain where errors come to. There's an error, something we're doing to deal with error in this. Okay, and we've done it without even thinking about it. I want you to think about where that came from. Okay, so it's a pretty complicated assignment. It's due on Friday, and if you have any questions, feel free to send a Teams message. Okay, where is it? There it is. Okay, feel free to send me a Teams message, and have fun graphing. Okay, I'll be talking to you later. See you guys.